Okay, Dr. Mark Norris,
Right.
welcome and over to you.
Thank you. Well, thank you very much for the introduction and the invitation to talk to you. I just put this slide up because it's almost contractually obliged, and also because when I'm talking to groups like yours, I find it a very fertile hunting ground for people who might be interested in not just undergraduate distance learning degrees in astronomy, but also postgraduate. We do masters by research and PhDs by distance learning, and we actually get some excellent students from the astronomical societies. So I always make a point of pointing that out because I've got some excellent students that way in the past. Now you've actually just heard most of what I wanted to say about me is by way of introduction, but my background is that I am an observational astronomer primarily, although I dabble a bit with applying simulations. My degree and PhD was at Durham, which is where the dabbling with simulations come from, because it's one of the sort of central locations where big simulations are done. I did postdocs at the University of North Carolina, Chapel Hill, and then at the Max Planck Institute for Astronomy. And much of what I'm going to be talking about tonight actually stems from work that started back in 2015 when I was still at MPIA. At the moment, like I say, I'm a senior lecturer at the University of Central Lancashire. I sort of run the Alston and Moor Park observatories. So you're quite lucky. You've got Bayford or whatever nearby. Alston is sort of a similar setup. We actually have one of the most powerful telescopes in Britain at the moment. We have a 70 centimeter plane wave CDK 700 and a very wide field imaging plane wave telescope as well that allow us to do a wide range of actual science as well as project for students. So if anyone's interested in a trip and a visit, we are always welcome to put on visits for groups. We don't charge. We even have our own little planetarium. So, and that's just a view of the place from above. Okay, so on to my topic, hunting the ghosts of galaxies. So one of the goals of astrogalactic astronomy these days, really forever, has been to understand how galaxies form and how they evolve. So principally what that really means is trying to understand the physics that allows you to take the really simple initial conditions of the Big Bang, which we understand with really exquisite detail, how we go from that almost uniform universe just after the Big Bang to the very complex universe we see today with these structures on all sorts of scales between sort of planets and superclusters of galaxies. So that's essentially what we're aiming to do, and it's not a straightforward task, that's for sure. There's a lot of physics in there. Now, traditionally, the way we would make progress in this field is that we would rely on technological breakthroughs. So you'd get a new technology, and that would open up new wavelength regimes, or it would increase your multiplex, or increase the signal to noise, or the sample size in some way, and then that would allow you to find some new phenomena that you weren't expecting to find. And so until recently, that meant that basically everything in astronomy was discovered by accident. Very few things were predicted in advance. It would be just we found a new technology and then we blundered across some new kind of object that was only visible in a certain wavelength, or at least was discovered in a certain wavelength. Now, things have started to change recently because the sort of simulations people do of the large scale structure of the universe are beginning to get increasingly detailed. And on top of that, they're building the statistics now such that you're not just simulating one galaxy, you can be simulating 100,000 or 1,000,000 galaxies forming in one of these large scale cosmological simulations. And these simulations are now producing reasonable reproductions of real galaxies. So those pictures you can see there, they are all simulated galaxies. They come out of this simulation called the Eagle simulation. And you could see the famous Hubble tuning fork of simulated galaxies. So on the left-hand side, you have your early type galaxies like your ellipticals and S-zeros, and then you go into your spiral galaxies and your barred spirals on the right-hand side of the thing. And then there's some irregulars down below. So these simulations are potentially producing tens of thousands, hundreds of thousands, millions of simulated galaxies that look increasingly close to the real galaxies we see in the universe. And because of that, they're beginning to make some predictions, basically. They're beginning to find things that observationally are difficult or were difficult to probe to determine if that was true. And so the classic example here is the fact that we have developed an understanding over the last sort of 15 years or so that galaxy formation has to be thought of in terms of two distinct phases and processes. The first is just the initial early phase, which is dominated by star formation in the galaxy that you see those stars in. So a galaxy like the Milky Way, that will be the dominant form of star formation throughout the Milky Way's life. It will just bubble along quite nicely, forming 1 to 4 solar masses of stars per year in a galaxy disk, and those stars will stay where they form, more or less. But there's also a second phase of the galaxy assembly process, which is that after you've formed big galaxies, their gravity will begin to attract smaller galaxies, and they will begin to pull them in, tear them apart, and acquire the stars that were previously in those smaller galaxies. So we call those stars ex situ stars. They're stars from outside the galaxy in which we currently see them. And so this is a little video of the Eagle simulation, and it shows some dark patches which are slightly over dense regions in the very early universe. And as the simulation goes on, gravity does its thing. A region that has slightly more matter has more gravity, so that allows it to attract even more matter, and the rich get richer. The slight overdensities in the universe become more and more overdense relative to the regions around them, and they are where the dark matter and the gas accumulate and eventually begin to form stars and hence galaxies. And so we've zoomed in to a single galaxy here, and what you're seeing is a lot of gas spiraling around, and eventually it will form what looks like a regular spiral disk, and stars will be forming in that disk. But you can also see that at the same time, there are large numbers of wispy little things falling in. They are the dwarf satellites of that galaxy, and they are gradually being disrupted and having their mass added to that spiral galaxy. You can see bigger ones just come in or fly off. Eventually, it'll come back, and its gas has already been acquired by the larger galaxy. So that is a process that the simulations very much see everywhere. And what we see is that that merging is somewhat essential to explain the formation of galaxies. What this plot here shows is just something simple, which is the stellar mass, the mass and stars of a galaxy against the size of a galaxy. And it's showing a plot of galaxies as they were seen 3 billion years ago. And it's split here into two populations, the ones that are forming stars, the spirals, the blue dots, and the ones that are dead, the early type galaxies, the ones that even 3 billion years ago had run out of gas, stopped forming stars, and turned into what we call red or dead galaxies. And so little compact galaxies are down there, and very big, massive galaxies like M87 live up there. They're both extended and more massive. But if we look back in the past, if we look at very high redshift galaxies, what we find is those dead galaxies, or the dead galaxies, at least at that period in the universe's history, at the same mass, they were quite a lot more compact than they are today. They were, factors of 5 or 10, maybe smaller than they currently are at the same mass.
Yeah, that's a bit late.
And what that means is, in practice, that there must be something to puff those galaxies up, because once you've made a compact galaxy, the stars can't just decide to move outwards on their own. There has to be some process that either pulls them outwards, or you have to add mass to the galaxy to the outskirts, which makes the size and the mass grow over time. And the reason that's particularly interesting here is it's affecting the red and dead galaxies. It's affecting the ones that can't grow by just building their own stars. So if those dead galaxies at a redshift of two or three-ish stay dead until today, the only way they can possibly have got bigger is if they have stolen stars from somewhere else, because they weren't making them themselves. So they have to move from essentially there to there over a period of 10 billion years or so. And so simulations do show that that is a process that could be generally going on. We call these types of mergers that do this generally dry mergers, because the galaxies that are getting gobbled up, they don't bring in any gas. So they're not adding gas to the galaxy that's already there. They're just adding stars that already existed. And this is a particularly quick and efficient way of making a galaxy puff up, making a galaxy bigger. Because if you take a big galaxy and then you just throw a little galaxy at it, the stars of the little galaxy will tend to end up on the outskirts of the bigger galaxy. It's very, very difficult for stars to lose orbital angular momentum and spiral into the center of the bigger galaxy. So they tend to stay on the outskirts. And because they tend to be being added to the outskirts, that has a strong effect of making the average size of the galaxy appear to expand quite quickly. So throwing a load of stars from other galaxies onto bigger galaxies is one way that you can puff them up over time. So my former PhD student, Tom Davison, he examined those simulated Eagle galaxies, and he confirmed a previously known result, which is that if you look at a sample of galaxies and you look as a function of stellar mass, you will find that the more massive a galaxy is, the larger the fraction of stars that were accreted will become. So for galaxies like the Milky Way, it might only be 5 or 10% of the stars of the Milky Way were accreted, could even be a few percent. But for a big galaxy like M87, it could be 50 or 80 or 90% potentially, according to the simulations. So that would be quite a profound change in how we understand galaxies if 80% of the stars you see in a galaxy come from actually much smaller galaxies initially. Now, Tom did something else that proved to be very interesting. He didn't just plot the galaxies as a function of their um, mass, he plotted them as a function of their mass and their size, because there is that trend we saw before that more massive galaxies tend to be more extended. And what he did was bin the galaxies. So each of these little hexagons has, 10 or 20 galaxies of the same mass and size. And then he averaged the ex situ fraction, the fraction of stars that were accreted for each of those 10 galaxies, say. And what he found interestingly was, yes, you get the trend that as mass goes up, the color changes and it becomes lighter and lighter, telling you that the accreted fraction is increasing. But also what he found is if you go at fixed mass and then go up over, you find that the more extended galaxies of the same mass, they have accreted a larger fraction of their stars. So here at say 10 to the 11 and a half, you go from maybe ex situ fractions of 40% to about 80% at the top end of this distribution. So they've doubled the fraction of their stars that they accreted. And that if you split the galaxies just into simple thirds, so third of the most compact, the third most average, and the third most extended galaxies, you really see that this is a significant effect. The bigger the galaxy is at fixed mass, the more stars it will have accreted. And, that makes sort of sense actually, because the stars are generally deposited on the outskirts. And so if you're accreting more stars, it would tend to make your galaxy appear larger than it would otherwise be at fixed mass. But the problem is, can you prove that? This is some really nice simulation work, but how do we actually go out into the real universe and prove that that's the case? So in the era of the Gaia satellite, it is possible to do some really phenomenal work with the Milky Way. So with Gaia, and with the missions that have followed up Gaia by getting spectra of millions of stars in the Milky Way, what you can do is build maps of stars where you know their distance very accurately, and then the spectra tells you their chemical composition very accurately. And if you combine those together, what you start to see are families of stars whose orbits show that they are similar orbits, and they have very similar chemistry, so very similar chemical fingerprints, indicating that the stars almost certainly formed in the same object. And so what we believe these arcs and curves and things across the sky are the tidal remains of dwarf galaxies and some star clusters, globular clusters in some cases, that the Milky Way is currently in the process of accreting and tearing apart. These are just the most recent ones where those tidal features remain quite tightly defined. So we now know of something like 20 of these around the Milky Way, and some of them extend to very large radii. Some of them are quite clearly associated with known objects like the Sagittarius dwarf galaxy, and some are associated with disrupting globular clusters. So using this will eventually, when all this analysis is done, be possible to put a fairly reasonable constraint on the amount of the Milky Way stellar mass that's been accreted. But that's a sample of one, and anyone who knows any statistics knows that a sample of one isn't a sample. And so you're not really constraining any models just by looking at the Milky Way. In fact, it's even worse than that, because if you look at Milky Way-like galaxies in the Eagle simulations, you see that the expected ex situ fraction, the accreted star fraction, can vary by a factor of almost 10. So us putting 1 point on that graph really doesn't constrain those models at all. What we need are large statistical samples that we can average together to find the overall trends, not just one object. So the question is there any hope to be able to examine other galaxies in the same detail that we're able to examine the Milky Way? The answer to that, unfortunately, is no, there isn't. Even with the JWST, galaxies are just so far away that we lose our ability to resolve the individual stars. And even if we can resolve a handful of the stars, what we can't do is measure them and get spectroscopy that would allow us to do this chemical abundance analysis that we need to do, not on a star by star basis. You can just about do it for things like the Magellanic Clouds, the dwarf satellites of the Milky Way, but beyond Andromeda, it's basically impossible, and it will remain so even when we get ourselves in ELT, or at least it'll remain extremely hard. So what can we do? Well, one of the first ideas people had was that we could try and use stellar streams in other galaxies. That is, just literally look at other galaxies and see, do we see any of these arcs of stars tracing across the halo of the galaxy? And you would sort of naively assume that the best way to do that is to get one of the big telescopes of the world, the ELTs, the VLT or the LBT, that kind of thing, and collect as much light as you possibly can. It turns out that's actually not the right way to do this. If you want to find faint features around other galaxies, what you actually need are relatively small, almost in quote marks, amateur setups. In particular, what you want are refractors, not reflectors, because the optical path is much more straightforward. Your point spread functions and your reflected light are much more well behaved, and you get much smoother backgrounds, and so you're able to trace out stellar streams to much fainter levels. You still have to image for hundreds of hours potentially, and then add it all together, but it's possible and it's much more achievable than using a big telescope in general. Now, surveys of thousands of those galaxies have now started. I mean, it's worked out even, we've done some of ourselves. And what we find is basically if you obtain deep enough pictures, basically every galaxy you look at will have some tidal debris around them, demonstrating that there are ongoing mergers right now. The problem, though, is that studying those stellar streams is still extremely hard. We're talking about surface brightnesses of 28 magnitudes per square arc second at best, and can be 30 or 31. Those are the kind of levels that just are not achievable easily. You have to do, like I say, hundreds of hours. And so you can only detect the brightest streams. The other downside is the streams themselves are not very long-lived. They'll last a few passages around the galaxy, and after that, they'll tend to smooth out, and you lose your ability to detect it as a stream. You'll just see a smooth structure that looks like, the outskirts of a galaxy. So finding it as a stream is difficult. And the last thing, the thing that's a real kicker, is these things are so faint, you can't even measure color. You have to use luminance filters, very broad filters generally, although there are some techniques to try very narrow as an alternative approach. But essentially, you can only measure how much light there is. You get no knowledge of how much red versus blue light there is. And so it therefore becomes very difficult to learn anything about the ages of the stars that are in that must be in that stream, or the metallicity of the stars that are in that stream. All you can really do is see that there's some light there and infer a sort of mass from that light by making a few assumptions. So it's useful, but it's not detailed enough for what I want to do. And so that leaves us what we call the integrated light of a galaxy. When you look at a galaxy, they are so far away, you see just this whitish glow, except that in every pixel of that image, that white glow is actually the light of tens of thousands, millions, perhaps billions of stars all added together. And so the question is, can you take that light, can you take that mushed up light, the sum of potentially millions of stars at a time, and can you use that to learn something about when those stars were born and what chemical composition they must have? And the answer is yes, using something called stellar population synthesis models. They will allow you to estimate how the luminosity of that bunch of stars, how the color of the stars, how the surface brightness evolve over time. So what's SPS? Well, the ingredients of an SPS model are relatively straightforward. You start off with something called the initial mass function. Now, that's the distribution of masses that stars have at birth. And what we find is this seems to be roughly universal. It's certainly pretty much universal across the disk of the Milky Way. There's some debate about whether it's universal when you go to other galaxies, but even if it varies, it shouldn't vary dramatically. What we see, and you can sort of see that in this picture here of a star forming region, is that there are many more faint, therefore lower mass stars than high mass stars when you form stars. You might have 100,000 low mass stars for every one massive star. And so you take that initial mass function, which, as I say, is pretty much the same across the Milky Way disk, and then you use what we know about how the mass of a star is related to where it will lie on something like the Hertzsprung-Russell or the color magnitude diagram. And so this plot here just shows you the main sequence where stars live during the main bulk of their lives, and each of the numbers along the way, those are stars of different masses. So where it says 120, that is a 120 solar mass star. Where it says 0.1, that is a zero point 0.1 solar mass star. And this is roughly where they will lie when they're born. And what you can see is there are two parameters here, luminosity and temperature, which are related or correlated in this plot. And you can see that as you go up in mass, your surface temperature of the star increases, but your luminosity increases dramatically. So you see the sun there at 1 solar mass. By definition, it has 1 solar luminosity. So we would say that has a mass to light ratio of 1. It is 1 solar mass divided by 1 solar luminosity, 1. But if we go up to a 2 solar mass star, that is twice the mass, but it doesn't have twice the luminosity. It actually has 10, 15 times the luminosity of the sun. And in fact, if you go all the way up to 100, 120 solar mass star, yes, it's got 120 times more mass, but it's got more than 1,000,000 times the luminosity. So what this means is the high mass stars are incredibly important early on because they're the ones that are producing most of the light. So we have the surface temperature, and we have our high mass stars up there, which are hot blue and short-lived, as we'll see. And down here we have our low mass stars, very small, very red, live a very, very long time. So as I said, the luminosity is related basically in this logarithmic way, such that, more massive stars are not just slightly more luminous, they're a lot more luminous. And it also means that the spectrum of the star will be modified too. That's for two different reasons. One, because you get the surface temperature and you get your black body curve which is the overall shape of a star spectrum. As the temperature gets lower, the peak of that goes from being in the UV or the blue to being in the red, and then in fact, for the very lowest mass stars, peaking in the near infrared. On top of that, the elements that are visible in the spectrum will also change as well. Even though these stars have exactly the same chemical composition, they have very different line strengths. Of these are dominated by hydrogen elements, hydrogen lines and helium lines. But as you go to cooler stars, you start to see more metal lines, things like magnesium here, iron lines here. I think that's sodium there. And if you go all the way to the very coolest stars, they're so cold that actually, I say cold, they're still like 2,500, 3,000 Kelvin, but their surfaces are low enough temperature that you actually get molecules that can survive in their atmosphere. So you get these giant bits of the spectrum eaten away by these molecules, like I think titanium oxide, things like that, even CO. Um, and that modifies the spectrum quite significantly. And the mass will also affect how long a star will live. So if you go to the sun, it will last about 10 billion years. If you go to the most massive star, even though it's 120 times bigger, so it has 120 times the fuel of the sun, because it's burning that fuel so much faster, it'll actually only live a few million years before it runs out of fuel. And at the other extreme, the lowest mass stars that are out there, they give out their energy so slowly that they can live maybe 1,000 times longer than the age of the universe so far. So what that means in practice is if you get to about 0.8 or 0.9 solar masses, no star lower than that mass has ever died in the history of the universe because none of them has ever reached the end of their fuel yet. And that obviously is going to have consequences for how the light output and the chemical enrichment of a stellar population will go. And the final thing that the mass of star determines, of course, is how a star dies. So at the high mass end, anything above about 8 solar masses, they're all going to go supernova, type 2 supernova, work quite rapidly. Anything below that is going to go through a planetary nebula phase, end up with as a white dwarf, potentially eventually have a type 1a supernova if it's in a binary system, but most of them probably won't. So how a star dies, and that will be important as well. And then the second important parameter that you want after the mass of a star is just what mixture of chemical elements are present in that star. Basically, as the universe has gone on, because there's been more and more supernova over time, the chemical complexity of the universe has increased. You've got more and more of the elements produced in supernova released into the universe. And so the amount of what we call metallicity goes up generally over time. And what this plot is showing you is essentially three spectra. The orange line here is the spectrum you would get if a star was just purely hydrogen. It would only have a hydrogen absorption line. It would have no absorption lines due to anything else. And the other two, well, the blue one, that is a star which has a metallicity that's about 1/10 as much as the sun's. And the red line is one that has a metallicity that is basically identical to the sun's. And what you see is that the one with the higher metallicity, it has deeper absorption lines, and therefore the chemical elements are affecting the atmosphere more strongly than they would in the one with fewer chemical elements. And this is something that's relatively straightforward to measure in spectra these days. So the recipe, what are we going to do? How are we going to make these SPS models? Well, what we're going to do is we're going to take our initial mass function and we're going to use that to distribute mass along the main sequence. So we have our low mass stars down here, we have the sun here, and we have our high mass stars up here. We're going to pick a metallicity, and all of the stars on that main sequence are going to share the same metallicity. And then we're going to populate that IMF so that we have a lot of stars down here, a few up here, and then very few along here. So this line looks like a solid line, but actually it's made up of individual dots, each of which is a single star. And at the top end, you begin to be able to see a handful of dots, because these are the stars, the massive stars that are going through the process of dying. They're going through what we call our blue loops. And those periods are, stars do not spend very long on those branches. And so you only see one or two stars at a time. So we have a lot of stars down there, few up here, and one up there. And then the clever trick. For each of those assimilated stars, we attach a spectrum to it. And that spectrum is one that's chosen to match that type of star. So it'll be the correct spectrum for, say, a star up there, which might be a B5V, a one down here, A0V, F3V, the sun, a G2V, so on and so forth. And we do that for every single star, and they're all weighted to be the correct luminosity for that star. And then we just add all of those spectra together. And what we end up with is the sum total of the spectrum of all of the million stars in that stellar population. So this is what that stellar population looks like for a solar metallicity stellar population that's 63 million years old. You can think of this very much as being like the spectrum you get if you found a globular cluster that was 63 million years old and you added up all the light. Because all of the stars we have here, we assume are formed at the same time from the same gas cloud with the same chemistry. So that's what it looks like after 63 million years. The clever bit is you then say, well, okay, let's evolve it for a bit. And after 100 million years, the most massive stars have died, and the slightly lower mass stars are now evolving off the main sequence. And you repeat the process, and you get the second spectrum. And you can see already the spectrum has gone down in luminosity. It's got fainter because we've lost the light of those brighter stars. And as we go on, we will see that the spectrum gradually moves. It becomes redder over time. The peak of it moves to the red part of the spectrum because we are losing the hot blue stars up here, and we're getting our light more and more dominated by the light from stars like the sun, which are, orangey in this terminology. So then we get down to 5 billion years, 10 billion years, And that shows you the sort of range of possibilities. But just look at how much the light level has dropped. It's dropped by a factor of 100 or so since that population was first born. But importantly, the mass has not dropped by anything like as large a factor because these stars were a relatively small fraction of the total mass of the star cluster, but they produced a very large fraction of the light. So most of the mass remains actually in the low mass stars, which aren't really, producing a lot of light. So in 2015, I took those models, those SSP models, and I did a very early attempt at something called full spectral fitting, which is where you take your spectrum, whatever it is, like a galaxy, and basically you allow a computer to figure out what distribution of those models fits your galaxy spectrum the best. And so you take some of these 8 different ages, different metallicities potentially. I'm never sure why this order is the way it is. And then you use them to fit a real spectrum. And so this shows that you can't really see it, but underneath that there is a black line, which is the spectrum, and then the red line is the best fit model that that combination of spectra has given you. And this is the real example where we did it for real data with a real galaxy, and you can barely see the difference between the real galaxy and the models that we fit. And then the clever thing you can do is just say, well, okay, how much of each model did you have to add to get it to match what that galaxy light is telling us? And so the plot here is showing you the age of all the models, the metallicity of the models, and every plus is where one of those combinations of models exists, combinations of age and metallicity. And there are hundreds. We fit 400 or 500, I think, at the moment to these kind of models. And the color shows you the weight map. So the redder colors, they are larger proportions of the galaxy's light is coming from stars with those ages and those metallicities. And I showed 2 examples here because the one on the right, the object here, we were pretty sure that this thing was a globular cluster, just a boring star cluster that was just a single thing that formed on its own at the same time out of a single gas cloud. And lo and behold, our weight map agreed that basically it was consistent with a single age and a single metallicity within the errors. The other one over here, it was a thing that looked like a globular cluster, something we called an ultra-compact dwarf. But we, for other reasons, suspected that this was actually a galaxy. It was a nucleus of a galaxy that had drifted too close to a big galaxy, and then the outer parts had all been torn off, and it left behind something that looked a bit like a globular cluster, but it was in fact, a galaxy. And because of that, because it's a galaxy, it can form stars over a long period. And that's why in this one you see stars that have ages that span anything really from about 10 billion years to about 3 billion years ago when we think the merger probably happened. So this was like the smoking gun of this thing being formed in a merger event. So we were very happy with that. Um, then we started thinking a bit further and going, well, what else can we learn from this technique? And what we realized was that if you had the distribution of the ages and metallicities of stars, you could actually figure out which ones had to have formed outside the galaxy you see them in today. And that's because of an observation that, not that many people are aware of, but it's an important one in galaxy studies. And that is, if you look at galaxies, there is this thing called the mass metallicity relation. This is an observed trend that the lower mass galaxies have lower chemical abundance. They have less complex, lower amounts of iron and magnesium and what have you, whereas the higher mass galaxies have much more oxygen and iron and carbon and all that sort of stuff. And the traditional explanation for what's going on there is these low mass galaxies are low mass and therefore they have quite small gravitational potentials. And when they have supernova, the supernova actually can blast the enriched material clean out of the galaxy. And so the galaxy doesn't enrich in metals very quickly because every time it has a supernova, it loses a large fraction of that material to the intergalactic medium, and it doesn't come back quickly and form new stars. The high mass galaxies, they're incredibly big. They have a very large gravitational potential. So when their supernova go off, the supernova ejector all stays in the galaxy and enriches gas clouds, which then form the next generation of stars, which are therefore more metal rich. And so they get more and more metal rich quicker and quicker. There's also an observation that's quite important, which says that the biggest galaxies form very early in the history of the universe and actually very quickly. The the period over which they form stars might only be a billion years or two. But as you go to lower and lower mass galaxies, the average age of the stars in those galaxies is lower. In other words, they form their stars later in the life of the universe, and they form them over a much longer period. And that's just related again to gravity. The very big galaxies, they sit at the bottoms of these very rare, very overdense regions of the universe, and they can accumulate their gas very early and form stars very quickly. The lower mass galaxies, they are in the regions that are not very strongly overdense, and it takes them a long time to basically be able to corral enough gas together to be able to start to form stars. And even when they do, their low mass means that as they have their supernova, they lose a lot of the gas every time they form some stars, and they have to wait for the gas to cycle back and form a next generation of stars. So they just take much longer to form their stars. So those two observations are key. Low mass galaxies form their stars over a longer period, and they're much lower metallicity. And what that means in practice is if you plot the ages and the metallicities of stars, there are regions of that parameter space that just cannot exist in big galaxies. So if we look today at the Milky Way, it is forming stars up here. It's forming stars that are more metal rich than the sun, because the sun formed 4 or 5 billion years ago, and zero age. It is impossible for the Milky Way to form any stars with 1/100th of the metallicity of the sun, because there is no gas in the Milky Way that is that low metallicity. So if you see stars down here in the Milky Way, they have to have come from outside. And in fact, you can plot these lines of how the metallicity evolves with time in any galaxy of a given mass, and they give you trends where you say, well, okay, anything below this line had to have formed in galaxies that are less massive than 10 to the 7. This line had to have been in galaxies less than 10 to the 8. This line, 10 to the 9, 10 to the 10, 10 to the 11. And so you can work out from where you find stars on this plane whether or not they are consistent with being formed in the galaxy you currently find them in. So we did some testing of that and found it was actually, potentially, as long as you can measure this accurately in real life, extremely accurate. It could tell you not just what fraction of stars were accreted by a galaxy, it could tell you what mass function those dwarf galaxies that were accreted had. In other words, how many of them were 10 to the 6, how many of them were 10 to the 7, how many of them were 10 to the 8. And so it could be incredibly powerful. But the testing had only ever been done with simulated data. We never tried it with real data. And so Tom, he went ahead and we tested this. And so we took this amazing beast of a machine here, Muse, which I know it looks like something out of the Matrix. And that's what's known as an integral field spectrograph. It lets you take a spectrum across a whole 2D image. So you can get, in this case, thousands of spectra from a single galaxy. And Tom tested this technique on this first galaxy, NGC 7135, because it has a very obvious tidal feature running through it. And so the question was, if we do this spectral technique, this SPS technique, is it possible for us to identify the population that is in this tidal stream as being different from that of the galaxy that we see it in? And the answer was yes, we could. It was really obvious. So these panels are each representing different regions of that um, galaxy. A is the center of the big galaxy, and at the center of the big galaxy, in common with basically all big galaxies, the stars are all old, and very metal rich because they're right at the bottom of that deep gravitational potential well. But points B and C, they're actually along this tidal stream, and what we see there is that there are stars that are much younger and still quite metal rich, but much younger. And on the other side of the galaxy, there was this little blob down here, which we hadn't really paid any attention to, but we took a spectrum, obviously, of the center of it, and then this little arc here. So that's K and H. And we realized that K was actually the nucleus, the center of the dwarf galaxy that is being destroyed. It's coming through here, it's gone to here, it's turning around again, it's coming back, and that is the very center of the galaxy that's being disrupted. It also has quite a high metallicity and old ages, but it also has a population that goes to younger ages. And then H, this plume of material here, which is miles away from over here, it's basically exactly the same as the tidal material over here. So the material here and the material here is identical, and it's very different to the stuff that's associated with the galaxy itself, which is D, E, and F. We also found another population which we weren't expecting, which is this clump down here. We see it in basically most of the panels. And what Tom was able to do was actually break the galaxy down into three components and build maps of where the stars were. And he's able to show that that ongoing merger has preferentially dumped its stars at larger radii around the galaxy, whereas the galaxy itself is very much symmetric and centered on the center of the galaxy as we expect. But that region down there, that seems to be associated with a merger that happened probably billions of years ago that we are able to pick up the remains of using this technique. There would be absolutely no other way that we could figure out that that had happened other than by looking at this and knowing that that population does not make sense relative to the others we see in that galaxy. So we're able to do that, and we went off and looked at a sample of 13 other early type galaxies, and the really nice result is this one here. So remembering that we had this prediction that as mass increases, the fraction of accreted stars increases, and at fixed mass, as you go up in size, the fraction that was accreted increases. What Tom found is basically exactly that. It's clearest for this one. What we did was look at the center of the galaxy and then look at the outskirts of the galaxy. And at the center of the galaxy, basically all galaxies are dominated by the stars that were formed in the galaxy itself. But on the outskirts, that's where your dumped accreted material preferentially is, and the accreted fraction there goes up dramatically, and it follows the trends that we just pointed out. As you go up in stellar mass, the fraction of stars that were accreted increases, and as you go up in fixed at fixed stellar mass, the fraction that was accreted increases as well. And the overall fractions that we see, they're not quite 80%, but we were seeing that some of these galaxies were accreting 40 or 50% of their stars, probably over their lifetime, or at least so far. So, conclusions. Well, the simulations have made a prediction. They made a prediction that galaxies form through two processes. The creation of their own stars, and then the acquisition of existing stars from other galaxies. And using this full spectral fitting technique on essentially single spectra often of galaxies, we're able to put pretty strong constraints on the accreted fraction. And so far, it definitely looks like the observational results are bearing out what the simulations say. We're maybe not getting exactly the fraction that they are, but the trends overall are consistent. And so it does look like for the biggest galaxies, things like M87, we probably have to rethink their formation. Something like M87 at the bottom of a deep potential well, like a galaxy cluster, you might well have to think of something more like a trash can. It's just got the detritus of a lot of other galaxy that's been tossed into it over the past 13 billion years. And that does impact how we understand those galaxies because um, all of their properties have to be weighed now with the understanding that, yes, it might be 500 times more massive than the Milky Way, but 250 times or 250 times the mass of the Milky Way probably was made in Milky Way sized things and smaller that were then added to that galaxy. It wasn't that it was, all formed as one giant thing. So I'll stop there and I'll take any questions anyone might have. That's all right.
Thank you. Thank you, Mark. That was wonderful. An awful lot to take in there.
Yeah.
But we'll begin as we always do. First of all, as if it were a live audience, we'd give you either a virtual or a real. Put your cameras on, everybody, and go back to your audio. And a big round of applause for Dr. Mark Norris. Thank you very much indeed. Thank you. Let me just change my view so I can see everybody. Um, yeah, that's a lot of that is really, beyond my ken. I have to be honest. I followed most of it, but it's tough stuff. But I understood most of it, but I would be wrong to say I understood all of it. But thank you for that. There's a lot to think about there, Mark. Just going back to the very beginning, the those simulations of the massive gas accretions forming those huge filaments, which eventually coalesce and become proto-galaxies, if I've understood that correctly.
Yeah.
You mentioned the spirality. You could see the gas forming. Obviously, the distances are immeasurable and unconscionable for a human mind. But we're talking about massive extensions of gas which accrete into. Typically, you were showing that sort of familiar pancake
Yeah.
sort of shape, and the spirality was already beginning to evolve. But
Yeah.
as I understood it, at that point, we're still talking about gas clouds, albeit massive gas clouds, not just a nebula, but a proto-galaxy. And
Yeah,
that's,
they will be forming stars as they are falling in. So the process, especially early on, while it's getting assembled,
yeah,
the earliest phases, those clumps will be forming stars, and especially when they hit each other,
sure.
because that increases the density dramatically, and that will drive up the star formation rate.
Yeah,
It's a very complex process because once you start forming stars, you start getting what we call feedback, right? Which is to say the stars shine and they give out
uh-huh,
good amounts of UV, and some of them start going supernova, and the energy from that begins to resist you being able to put more gas in, if you see what I mean. Uh,
yeah,
this is why galaxy formation is such a complicated process. If it was just gravity, it would be really simple. But the minute you have basically nuclear fusion involved, you get feedback, and that begins to affect things in ways that you don't usually expect,
mm,
don't fully understand yet, even, I would say.
sure. But I mean, the spirality is one that's what most people think of as a galaxy, is that sort of flat disk and
Mhm.
that spiral shape, be it barred or spiral
Yeah.
or even elliptical. But what about globular? I mean, there are some gigantic galaxies out there which are
Well,
purely globular. And I'm not talking globular clusters. They are effectively clusters, but they're gigantic enough to be called
so
galaxies.
M87 would be a perfect
Yeah.
example. What we'd call an E naught galaxy, a very round
Yes.
type galaxy. Um,
How is the accretion explained for that then, as opposed to the spirality?
this would be naturally explained by this merger process, right? Because if you think about a merger, there's no preferred direction for a galaxy to fall in.
No.
So you're essentially randomizing the orbits of the stars. So imagine you built an M87 out of hundreds potentially of Milky Ways falling in at random angles. the net result is you're going to get something that
Yes.
round. What we do find is that other early types that are flattened, they generally are flattened because there is some rotation present. So there might have been a preferred direction, and also don't discount that half the stars did form in situ, and so those
Yes.
ones will have formed where you have to conserve angular momentum in the gap,
Yes.
like a disk does,
Yes.
and you disrupt that over time with the stuff you're chucking on top of it, if you see what I mean. So
Yes.
what might have been originally a bit more flattened gets puffed up and turned
Yeah.
into a spherical
Yeah.
distribution. But yeah, the merging certainly helps with that. The spiral arms are, just as we say, absolutely fundamental. If you get gas together and you get stars forming, your gas, the conservation of angular momentum is what gives you a disk. And
Yeah.
once you've got that, these spiral density waves are basically inevitable. Um, slight torque here or there, and then gravity just will essentially exacerbate any underlying
Sure.
asymmetries.
But if there's no predominant, uh, for want of a better word, angular momentum in the initial gas accretion, and it's being bombarded, as it were, from all sides, then you're not guaranteed this spirality, and you may get a lenticular or globular cluster or whatever, or galaxy, I should say, is
It,
what
it
you're
very much
saying.
depends on the mass. So
Yeah.
remember again, spiral galaxies like Andromeda and the Milky Way were pretty big for spiral galaxies actually. Getting towards the top end of what a spiral galaxy can be.
Oh, really?
Uh,
Even the Milky Way?
well, this is an interest. If I was telling you this 6 months ago, I'd have said no. But I read something the other day that people are again arguing about which is bigger in terms of mass, Andromeda or the Milky Way. And for a long time, everyone said Andromeda was like 50% more massive, but it seems like the Milky Way Andromeda might well be about the same again. So
It's just the population that differs, but not the mass.
it is definitely physically bigger.
Yes. Yes.
Andromeda it is physically wider,
Yeah.
but based on the kinematics, potentially they're very similar in total mass. Even
Okay.
if they're not, 50% is not a big deal anyway. This is astronomy factors of 10,
Yeah.
what we care about. Um, so you can go a little bit bigger than that. But after that, you don't get spirals anymore. You get S zeros. You seem to have a process where once you get too big, your halo it inhibits the accretion of gas called gas that can form stars anymore, and you end up transitioning from being something that can form stars to one of these red or dead galaxies.
Mm.
The usual explanation is you have a very deep potential well and you drop a gas cloud onto it, right? If the potential well is hot deep enough, well, you're dropping something, right? So it's falling, a gas cloud that's falling. If it falls fast enough, that gives it a lot of kinetic energy. And that kinetic energy goes into the temperature of the gas. And
Yeah.
eventually, if the potential well is big enough, the amount of energy you put in just by dropping something into a galaxy cluster is enough to heat that gas up to 1 million degrees. And then you can't form stars with 1 million degree gas.
No.
So once you get above um, 10 or 50 times more massive than the Milky Way, something like that, there's a definite point where your amount that you can form stars drops off a cliff. And you
Yeah.
have to rely on this process, accretion, to make yourself more massive. Yeah.
Okay. Yeah. Well, I'm going to hand over to the floor and ask members to ask questions as well. But just before I do, um, just an observation, really. It's not so much a question, but the simulations and the models you're using, it's amazing to see that you're able to model completely artificially, but based on maths and algorithms, the famous Hubble tuning fork, that it actually came up with that split and those, developing from the globular to the, the classic spiral and then the barred spiral.
You have to be a little bit careful. There's absolutely no evolution in that plot, right?
No,
People believed that he had it the wrong way around if it was anything.
uh,
But yeah, it is impressive that they are able to reproduce the shapes. Now, don't get me wrong, there are still problems. Like the galaxies tend to be, the disks tend to be twice, two times too thick, things like that.
mhm.
But each generation that these models are run, which generally happens every 5 years or so, because
Even so, it
computing
is
gets
impressive.
closer and closer. Yeah, absolutely.
Okay, I'm going to hand over does anybody have a question for Mark about tonight's talk?
Yeah, I've got one. So what's your next challenge, Mark? Now you solved that one.
Well, I wouldn't say we solved it. What we're working on at the moment is the technology, the code we use to do the fitting was actually developed for something completely different. It was developed to figure out the motions of the stars in the galaxy to work out how fast the populations of stars are moving. So it's not really optimized for the task. So I've got a student who is actually a mature student, distance learning, who's doing machine learning to disentangle the spectra. So you feed the machine a series of simulated galaxies and their simulated, their age and metallicity distribution and the spectrum that that results in, and you let the machine learning code figure out if I have this spectrum, what distribution of age and metallicity must have given me that. And terrifyingly good so far. Um, Complete black box. We have no understanding of how it works. It just seems to work really well. And I'm an observational astronomer, which makes me an empiricist. So I don't care how it works as long as I'm confident it does. But yeah, it is kind of hot, terrifying how good it works without us having any understanding of why it works.
Oh, yeah.
Essentially, must be picking up very subtle features in the spectrum that just we're not capable of understanding. So that's
Yeah.
what we're working on next. And the other thing is, we did have another paper recently where we had another prediction from some simulations. Actually, it made a prediction about. Are you familiar with compact elliptical galaxies like M32? It's the closest neighbor, one of the closest neighbors of Andromeda, actually.
One, yeah.
And it's a very compact elliptical galaxy, very small, like half-light radius of only 100 parsecs. And it's the prototype of this class called the compact elliptical that people have argued about for decades how they form. And the general consensus was they are tidally stripped, that they are bigger galaxies, quite large ones actually, with a bulge that drift close to something like Andromeda, and all the outer stars get removed, and you're left with just like the bulge behind, and it looks like a little elliptical going around. So we had some simulations to try and figure out, is that what's going on? And to our surprise, we found that 24% of them were formed that way, but 76% of them were formed a different way, in a way that we haven't observed yet. And so now we're like, well, can we go out and observe that? So can we find some of these forming this, what we call ram pressure cooking? Uh, so that's the next thing.
And where would you get that data from? Is that waiting for, it's not a web kind of thing, it's more of a.
It's fortunately we have quite a lot on hand because I've been studying CE since I was doing UCDs back in Max Planck, so I've got some good spectra. We need to redeploy these techniques that we've used on the bigger galaxies to these little galaxies.
Right.
That's one thing, but we will need a more statistically significant sample. What I've got is the usual classical thing when you start, you get some spectra of the most famous objects, but it's whatever was available when the telescope was free for us to use effectively, right? So
Yeah.
that not like we're fairly sampling the population. Now there are some new surveys about to start in the end of the year, one called Foremost, and we're in that, and that's going to get spectra of 6 million galaxies, and we should get thousands of compact ellipticals from that, and we will importantly get them fairly sampled. We'll get like them everywhere, not just in dense clusters, but in groups, and potentially, if they exist, in low density environments as well. So that'll be revolutionary, but that survey is going to take 5 years or something to run. So one for a couple of generations of my students to deal with.
Yeah, keep them busy, that's the way.
Yeah.
I've got a quick question. If I understand what you're saying, the initial sizes of galaxies very much depended on the amount of matter that was in their area. So you've got quite a range of sizes, and the bigger ones are potentially growing bigger because they can absorb more from outside. The smaller ones less so. Is that distribution of the size distribution changing significantly over time? Are there more bigger ones and fewer smaller, or
Not really. Well, yes and no. It depends exactly when you're looking. The smaller ones, so we have an observational effect, which is it's really hard to find the small ones.
right? Yes.
Really hard to find them at higher redshift, right? So we have this problem that we increasingly can only see the very biggest and brightest things observationally. But there will be some evolution, but not as much as you might think, because of that downsizing effect, just these tiny little things will grow to the point where they're replacing some of the things that are being lost, if you see what I mean. So there should be a sort of conveyor belt in the lower density environments where you still have access to gas. But in the galaxy clusters, no, there's galaxies fall in from outside of the cluster, but there's nothing forming in the cluster, basically.
As you said, the bigger ones, the less star formation, the smaller ones more so.
Yeah, exactly.
Yeah.
And you know, there's a real I didn't show the plot. There's a really fantastic plot that illustrates this very clearly. It's quite interesting. It's basically the ratio of the stellar mass in a galaxy to the dark matter of the galaxy. And why it's interesting is because there's basically a universal fraction of dark matter to gas, right? But that is not representative in the galaxy population. What it shows is actually Milky Way sized galaxies are the most efficient galaxies at taking what gas they get and turning it into stars. The low mass galaxies are very inefficient at turning gas into stars for the reason I said before. They're big supernova that blast the gas out and then they can't form. It takes ages for it to cool and come back and form another generation, right? The high mass end, they're horrifically inefficient as well, surprisingly.
Ah.
So they form a lot of stars because they've got big black holes, and whenever they get fed, they shoot
Just
energy
get eaten.
the gas. So on top of that, they live in these really dense environments where again drop something and it shock heats to 1,000,000 degrees and never forms any stars. So the galaxy formation process is, fantastically complex. I sometimes joke to our physics friends, like at least you only have to care about electromagnetics. Literally, if you want to understand galaxy formation, you have all four forces of nature matter. You care about gravity, definitely. You care about electromagnetism because of the effect of the feedback. Care about the strong and weak nuclear forces because you do care about supernova and fusion and the power sources of all of these
The
processes.
whole kit and caboodle. Yeah.
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 And on size scales that literally go from subatomic to
All
the whole universe. So
nice and easy then. Yes.
given
Yep.
that the physics itself should be relatively straightforward, it is
Yeah.
much more
Yeah.
complex because of that interplay between them.
Thank you.
Somebody else? Okay, I'm just following on from the idea of larger galaxies accreting stars from smaller galaxies and they eventually being broken up and effectively not being galaxies anymore. A very basic question, Mark, but I think I'm right in saying that we've observed that most only nearby galaxies we can see this, but certainly we know that there's something of the order is it a few hundred globular clusters in the galactic halo of the Milky Way.
Yep.
And our nearest big neighbor, obviously Andromeda, has many more than that. But if we set aside the aspect of mass that you just mentioned, which is very interesting, by the way, about them being comparable in mass terms, even though in population and size and diameter, Andromeda is obviously our biggest sister. But if we disregard that, morphologically, they are very similar as far as we know. Both spiral galaxies may be more barred or less barred, I don't know. But and they both have a halo and they both have these masses or populations of globular clusters. We have also several dwarf galaxies, most notably the Magellanics. I think there are others as well. You imagine, yeah.
2030.
I mean, what I'm really leading to, and it's a pretty obvious question and probably a dumb one, but we have a large galaxy, we have a small galaxy, and we have clusters. When does a cluster become a galaxy, and when is a cluster absorbed and accreted as well? Are we can
So
can we envisage
I
all
can
these?
answer one of those, right? And I'll tell you the other.
Okay,
I can't answer the other one. Uh, so of the Milky Way halo or Milky Way globular clusters, we actually think half of them came from accreted galaxies
okay,
because they do things like a large fraction of them counter rotate. They go the wrong way around the galaxy.
yes,
That's
which is
a
yeah,
big hint. But the others are actually in these tidal features that I mentioned. So the Sagittarius
see,
dwarf galaxy, actually the center of that is a globular. It's clearly actually the nucleus of that galaxy, right? And along the tidal stream are embedded several other globulars, which have the same chemistry basically as that galaxy.
yeah.
There's a really nice paper by some friends of mine, Bridges and Forbes, um, where they looked at that and came to the conclusion that probably half of the Milky Way's population is accreted. Probably similar fractions for Andromeda. So
So these are, so if I'm understanding, these are kind of spaghettified minor galaxies or smaller galaxies that
yeah,
have been drawn in and
so
accreted.
the point that why this happens is galaxies have dark matter, right? And the outskirts of galaxies require the dark matter. And when you have a merger, that dark matter is actually what gets stripped first. And once that gravity is removed, the outer stars are now moving too fast for the potential they're in. And so they
Okay.
get lost to space, right? But globulars, they don't have any dark matter. They are self-gravitationally bound.
Yes.
They're
Yes.
bound by their own stellar mass. So they don't really care. Usually, the galaxy sort of disrupts around them and they get left behind in these trails and the dissipating stars of the rest. And when they get very close, then the gravity tidal forces of the Milky Way do begin to pull them. I think Turzan 5 has these nice S-shaped things. But in general, no, they just get deposited on the Milky Way and survive. Now, to answer your other question, difference between a galaxy and a cluster, it's one of my favorite questions, because the answer is
Obviously not the first to ask this.
no, you're not. And the funny answer is there is no answer because we haven't got a definition of what a galaxy is. So I was involved. I think it was Duncan Forbes again, was involved. We had a thing amongst the astronomical community to have a vote on what a definition of a galaxy was. And the winning entry got about 40%, right?
Which isn't very convincing, no.
No, and the winning entry was something like a dark matter halo with some stars in it, right?
So there we are.
And so there were some people that would say, well, so a small fraction would say, well, even a dark matter halo with some gas in it is still a galaxy, or it will become a galaxy. So we should treat it as one.
Yeah.
And some
Yeah.
people would say, well, no, you can get these things called tidal dwarf galaxies which are formed actually in gas-rich mergers where some of the gas gets flung out and forms basically a self-gravitating galaxy, but it's got no dark matter because it was never its own potential. And so people will
Yeah.
say they're galaxies, but other people say, well, they're not really galaxies. They're like, it's basically there is no good definition, right? Everyone knows a galaxy when they see one, but
Yeah.
no one can write down what one is.
So it sounds as though there might be a future meeting of the IAU, and some
Um,
of the dwarf galaxies will get Plutofied, if you know what I mean.
yeah,
They'll be rejected or demoted or whatever.
it
Yeah, fascinating.
generally an interesting point, and even the globulars are not so straightforward because some of the globulars in the Milky Way are probably actually galaxy nuclei that were stripped out.
Mm,
Omega 7 is the classic example. It's much more massive than the Milky Way's globulars. And when you look at it, it actually has stars of different ages in it, which is a bit of a giveaway. Because again, globulars all form their stars at the same time. And this one seems to have formed multiple periods. And that can only have happened when it was at the bottom of a potential well,
yeah,
which it clearly isn't anymore. So
great.
yeah, it's an open question. It's fun to debate, but I've been at conferences where we've wasted time arguing about this, but I'm not going to lose any sleep over it. I know what a galaxy
No.
is.
Talking of sleep, I think after all you've told us tonight, Mark, I think I'm going to need a lie down. Actually. There's a lot to take in there. Thank you ever so much. I think we're done with questions. Has anyone got a burning question last time? Gone? I think not. I'm going to just switch off the recording.
Yeah.
Okay.